Okay, so let me say I'm delighted to be here giving this presentation, and I'm particularly delighted to have Ejan as the respondent. You didn't say this, but I've actually known Ejan for over 40 years, I believe. We first met, I think we first met at Stanford.
In the 70s.
Either 73, we're debating whether we met then, or certainly we met in 1975 at Stanford, where we were both there in the summer. And our two boys were about the same age at like 1.5. And so we got to know each other very well during that summer. So the title of the talk you see on semi-supervised learning of legal semantics. What I'm going to do is the talk will cover section 3 of a new paper of mine called Finding the Right Balance in Artificial Intelligence and Law. Actually, this is a chapter in a forthcoming book, which is, so I don't have a pointer, but if I want to point to something, can you see that cursor if I move the cursor down there? Okay. So the forthcoming book, edited by Woody Barfield and Ugo Pagallo, it's an Edward Elgar Press book, research handbook, that's a series that they have, on the law of artificial intelligence. Most of the chapters in that book are concerned with the law applied to or governing artificial intelligence in society. But my chapter, a bit of an exception, is the flip side of that topic because it's the applications of artificial intelligence to law. So if you look at section 3, that's the outline of my talk. There's a challenge that I'll put forth, 2 steps toward a solution, and that's basically based on 2 papers of mine from ICALE 2007 and ICALE 2015. And then the next step is basically current research that I'm doing, or more correctly, a proposal for addressing the challenge. There's lots of detail in section 3, and this talk necessarily is a brief overview. Think of it as a trailer for a feature film, and hopefully it motivates you to go back and read the full paper and fill in all the details. So current research, my goal quite broadly is to construct domain-dependent legal knowledge representation languages, either automatically or semi-automatically from unstructured legal texts. And I'm going to talk about first talk about 3 papers that go back 20 years. 1998, a paper called Structured Case Notes, How Publishers Can Add Value to Public Domain Legal Materials on the World Wide Web. And these 2 papers I mentioned from ICALE 2007 and 2015, which are the 2 steps toward a solution. And then I'll talk about the proposal for the next step. So this is from my 1998 paper, The Challenge. And the main claim of that paper was that editorial enhancements to primary legal materials should take the form of computational structures using recent advances in knowledge representation, KR, natural language, NL, at the time, rather than free-form natural language text, which has been the way most digests and commentary on primary legal materials has been handled for many years, centuries really. And the suggestion, what I defined there was what I called a structured case note. A structured case note is a computational summary of the procedural history of a case, along with the substantive legal conclusions articulated at each stage of the process. It would play the same role in the legal information systems of the 21st century that West headnotes and key numbers have played in the 20th century. And notice I said procedural history. Why? Well, this is from the paper. Think about the traditional brief that students are taught to write in their first year of law school. traditional case brief focuses on the procedural context first, at least this is the way we always did it in American law schools, and I believe elsewhere. Who is suing whom and for what? What is the plaintiff's legal theory? What facts does the plaintiff allege to support this theory? How does the defendant respond? How does the trial court dispose of the case? What is the basis of the appeal? What issues of law are presented to the appellate court? How does the appellate court resolve these issues and with what justification? And you can see how those questions are designed to focus the law student on what the lawyer needs to know about a particular case. That's why we always used it pedagogically. Within this procedural framework, we would represent the substantive issues at stake in the decision. Now that's more complicated because it's going to potentially encompass the entire legal system, but we can make progress if we focus on particular areas of the law one at a time. So for example, and this was an example that I used in that 1998 paper, we could focus on copyright law, and to make the point I discussed in that paper, what was then a fairly recent case with 3 decisions, the District Court, the Ninth Circuit Court of Appeals, and the United States Supreme Court, copyright case called Quality King versus Lanza Research. And in that case, the Supreme Court reversed the Ninth Circuit decision based on a disagreement about the scope of these 3 provisions of the 1976 Copyright Act. I didn't put this on the slide, but I'll just quote from the Ninth Circuit opinion. From the text of the 1976 Copyright Act, it is unclear whether Section 602A creates a right that is distinct from Section 1063 and therefore is not limited by Section 109A, or alternatively, whether Section 602A is merely an extension of Section 1063 and therefore is limited by Section 109A. And the Ninth Circuit chose the first alternative, the Supreme Court reversed and chose the second alternative. And the task for a structured case note, after embedding these issues into that representation of the procedural history, the task for a structured case note is to represent this choice in some structured knowledge representation language. That's the KR component. So that's what we want, I claim, in a structured case note. I think you can see why if we had that represented in a formal structured knowledge representation language, we could do, and we had many cases represented that way, we could do very powerful retrieval, search, analysis, comparison of cases. And so the question is, how can we build such a database at the appropriate scale, right? Because we're going to have thousands, hundreds of thousands of cases. And can we build structured case notes at the appropriate scale? Well, that's the challenge. 20 years ago, I tried to persuade people that they should be working on this challenge, including some prominent legal research companies, legal retrieval companies at the time, but I could not persuade anyone to pursue this at the time. But today, the ideas have attracted more attention, and I'll just give you one example, a commercial example. It's a company in California called Judicata. How many people you know the work of Judicata? Is anyone familiar with it? Well, you should look at it. It's a very interesting company. They're providing legal research tools, legal search tools. Here's the claim. Not all legal search is created equal. I'm not sure if you can read the small print here, but Judicata is ushering in a new area of legal search that is unprecedented in its precision, relevancy, and simplicity. And this is a comment from a commentator, but it summarizes correctly what Judicata is doing. The secret sauce in Judicata is what it calls mapping the legal genome, or mapping the law with extreme accuracy and granularity. It's actually interesting that Judicata actually has a trademark registered on the phrase mapping the legal genome. And examples, so when you do a search on judicata, the user sees aspects of this map of the legal genome by being able to specify various filters on the case. So examples are cause of action, procedural posture, role of the parties at trial, disposition, court, judge, and several others. Okay, now you can see that what judicata calls the map of the legal genome is very close to what I called the components of a structured case note. They have extracted some of that critical information, not quite as much detail as what I argued for in the earlier paper, but still, it turns out to be an extremely useful data structure, and their entire, I say that the user sees this as filters that they can apply to cases, but behind the scenes, judicata's system is using that map of the legal genome, quote unquote, to do all kinds of powerful things in searching and comparing and mapping cases. So remember the challenge: how do you build a database of structured case notes to scale, or how do you map the legal genome to scale? Well, how did judicata do it? Well, it took a lot of work. 5 years and $8 million investment so far, and they have so far only covered California civil cases. Now they intend to expand. I think New York is next of their state law jurisdictions. The claim is, and I know the CEO of this company. I've talked to him quite a bit. The claim is that having developed the software, okay, so I should say what they did. They did a substantial amount of automatic processing of cases. And remember that I say only California cases, but they've covered all California civil cases back to, I don't remember the date, but quite some time back. But then they've had to do substantial manual review and post-editing to get the accuracy that they need and to resolve nuances to get this information out. Okay, so it can be done. It's a costly, laborious process because of the manual review, and so the challenge is partially addressed by judicata, but there's still more to be done, because what we would like is we'd like to automate that as much as possible. We may still have to do manual review, manual cleanup, manual post-editing, but the more we can automate in the more greater depth and the greater accuracy we can do, the better we are, obviously, and we can expand a system like judicata to other jurisdictions, both state and federal. So that's the challenge. And now let me talk about 2 other papers, 2 steps toward a solution. This is my work again. This paper from ICALE 2007, and the context here is that, well, when I wrote that first paper in 1998, the field of computational linguistics was not advanced enough by far to handle the complexities of judicial opinions. But the state of the art changed dramatically, in my opinion, by the thesis, and many others, by the thesis from a PhD dissertation by Michael Collins in 1999. And so from the beginning, from which Michael Collins' parser appeared, I started working on applying it to legal cases and finally wrote a paper in 2007. And there were 2 contributions in that paper. First, I showed that a state-of-the-art statistical parser can now handle even the complex syntactic constructions of an appellate court judge. I did that simply by applying Collins' parser to a corpus that I put together of 111 cases consisting of 15,362 sentences. That's now a small corpus by today's standards, but at the time it was fairly substantial. Some were Supreme Court cases, but mostly they were Second and Third Circuit Court of Appeals cases in the United States. The second contribution, which I think was really more important, I showed that a semantic interpretation of the full text of a judicial opinion can be computed automatically from the output of the parser. So this was my contribution. I built what I called a quasi-logical form. I'll show you examples of that. And a definite clause grammar that translated from the Collins parse tree into my quasi-logical form, which was my semantic interpretation. So here's some examples of sentences in the quasi-logical form for certain sentences. Now, I'm not sure you can see I'm not sure how much of this example you can read because the type has to be kind of small. Here's a sentence. She has also brought this ADA suit in which she claims that her former employer, Policy Management Systems Corporation, discriminated against her on account of her disability. And now if we look at that, if we focus in on that sentence a little further, rather the quasi-logical form here, you'll see the basic structures of my quasi-logical form, my QLF. Everything is a term, and a term has three components: a lexical item, a variable, and a list of constituents. So here's a lexical item brought, here's a variable A, and here's a list of constituents. You form, I should say, there are four kinds of terms. There are S terms, N terms, P terms, and A terms. The S term is a relation, and it usually represents the predicate of a sentence or a phrase within a sentence. The N term is an object. The A term is a modifier, like an adjective or an adverb. And the P term is a binary relation, which is usually corresponds to a preposition. And then, given these four kinds of terms, you construct the QLF with two operations. One, you embed expressions in the list of constituents, so you can see that's happening here. And you adjoin expressions before or after a term, which are called pre-modifiers and post-modifiers. That's happening throughout here. And that those two composition operators correspond to the distinction in language between what are called complements and adjuncts by linguists. Okay? So here's another example. The petitioner contends that the regulatory takings claim should not have been decided by the jury and that the Court of Appeals adopted an erroneous standard for regulatory takings liability. I said that the S term usually represents the predicate argument structure of a sentence or a phrase within a sentence. So here we have decided and adopted, etc. And here you can see that the phrase decided is modified here, aspect of the representation that I didn't explain previously, by tense and modality. So we have tense and modality. Now, a high-level point here. I think if you look at this QLF and you look at the sentence that it represents, you can see that these terms convey some of the information that we want to know about a case. Decided and adopted are actions, and they are qualified by a deontic modality. That's clearly captured in the QLF. Contends up here is an epistemic modality. And if you think about it, both actions, modalities over actions, epistemic modalities, knowledge, belief, etc., that's sort of those are the ingredients of legal discourse. A judge cannot write an opinion without using all kinds of terms like that. And the first step in meeting the challenge of structured case notes is to extract that kind of structured information from the actual text of the case. Here's another example, and what's highlighted here, I won't go into it, is really showing you how the P term works and how possessives are handled, okay? And again, you can see that this is some of the information that we need to know, that we want to know about a case. The court ruled that sufficient evidence had been presented, et cetera, from which it reasonably could have decided. Okay. So we clearly have some components of the information that we want to extract from the case just right here in the QLF, right? But we have to put there's lots of pieces scattered around the text of the case. And we have to put all those pieces together to see the correct interpretation of the case overall, that is, the procedural history and the substantive issues. That's what we want in a structured case note. So we have to go further, and the QLF was actually intended from the start to be an intermediate step towards the representation of a structured case note in what I've called, for a long time, I've used it in a number of projects, a language for legal discourse, LLD, language for legal discourse. Okay? So, what's the next step toward a solution? Well, now we're talking about my paper fairly recently in ICAL 2015 with the title, How to Ground a Language for Legal Discourse in a Prototypical Perceptual Semantics. The original ICAL 2015 paper, by the way, all of these papers that I'm referring to, if you get a copy of the original article, the chapter, and it's available online. Just do a search, my name, the title, you'll find it. I posted it on LinkedIn. It's also, the repository is on ResearchGate. You can find it by any of those, simple search, it'll come up. So the ICAL 2015 paper, I've been told it was hard to follow. It had a lot of dense technical detail. So I produced two new versions of the same material for different audiences. So for lawyers, I wrote an article, I call it a longer and gentler introduction, although people have still struggled with some of it, I think. But I tried to make the technical details a little more accessible to lawyers, or at least technically inclined lawyers. In the Michigan State Law Review, for computer scientists and mathematicians, I gave a talk at the CUNY Graduate Center in Manhattan about a year ago, Probability, Geometry, Logic, a triptych for a learnable knowledge representation language. So that's a slideshow. And as you can see, the mathematical prerequisites are fairly stiff. But for AI and law researchers, if you want to go into this in more detail, I recommend reading the Law Review article and the slideshow side by side. And that should give you some insight. So I'll try to give you a little sense of the ideas here, but of course, you have to really read the papers to grasp the whole theory. So here's a schematic view of what I call a theory of differential similarity, which is presented in these papers. Now you'll see what we have here is a diagram that shows probability, geometry, logic, reading from the bottom up. Now, historically, AI was based on logic in its earlier incarnations. And more recently, probability. And there have been many attempts over the years to combine logic and probability into a single system. Some of them, I think, quite successful. Pedro Dominguez has done some substantial work on that. But what I'm adding, the new element here, at least it's new in this context, is the geometric component. Specifically, and I'll have to be a little bit technical here to convey the idea. Specifically, the geometric model here is a low-dimensional Riemannian manifold. That's a nonlinear subspace, a nonlinear Riemannian manifold embedded in a high-dimensional Euclidean space. And the way these pieces fit together is shown here in what I'm calling constraints. The logic is constrained by the geometry, the geometric model is constrained by the probabilistic model, and the probability measure is constrained by the data. Now, how does this work? What does this mean? Well, you really have to read the papers. But that's the trailer to the feature film, right? But I'll give you in summary form, without justification, I will make some assertions about several important properties that I believe this system has. Number one, it captures the open texture of legal concepts, and it models in its geometric layer the prototype plus deformation structures that I have discussed in my previous work. Well, what do I mean, prototype plus deformation structures? Again, the article, the chapter, gives you, that's from much earlier work that I did back in the, starting in the 1970s, but going well into the 1980s and 90s, trying to understand legal reasoning in terms of reasoning with prototypes and deformations or transformations of the prototypes. I think legal philosophers will appreciate this description. We understand legal cases by seeing prototypical examples of the situation that's being characterized, and we understand how other cases may or may not be classified by constructing deformations or transformations from the prototype. That's the intuition. Now, the way that that's captured in this new formal mathematical model is because the geometric model uses a form of what I call prototype coding. And you think about it this way. Think of a point in an n-dimensional space. We're going to represent that point in an n-dimensional space by measuring its distance from a prototype in several specified directions. And that is exactly what we do with this Riemannian manifold. Again, the papers will tell you more about it. But I'm trying to convey some intuition about what's going on here. That's number one. Number two, if you think about this stack that I had in the previous slide, probability, geometry, logic, you'll see that this model combines a rule-based model, that's logic at the top, and a data-driven model, that's the probability at the bottom, combines those in a principled way mediated by the geometric model in the center. That's the picture that you should have in mind. Okay? You may recognize this as a familiar dichotomy in legal technology today. Rule-based models, rule-based systems, those are the kinds of things that, for example, Neotologic builds. Data-driven model, that's the kind of systems that Lex Machina produces, for example. And the claim is, and many people have argued this, particularly for law, legal reasoning, and legal analysis, we need some hybrids that combine rule-based and data-driven models. And my argument my claim is that this model that I'm developing combines those two and is, in fact, a reasonable vehicle for the hybrid model that we want, combining rule-based logic and data-driven probability into a single framework. Number 3, it's not a neural network, but it does implement, and here in Montreal I may get myself in trouble by saying this, it implements a form of deep learning with multiple layers of unsupervised learning at the bottom and optionally a layer of supervised learning at the top. So, all right, in my ICAL 2015 paper, I illustrated this point with an image processing example, which is a very standard example using the MNIST data set of handwritten digits. But the general claim, still really to be validated, is that that idea can be generalized to my entire language or legal discourse. I need to do a little more work on that and develop that more concretely, but that's the goal. And then let me finally make another point. Again, think of this stack in that slide, probability, geometry, logic. Since the top layer is a logical language, the concepts that it learns are potentially interpretable. And this is a very big issue in AI applications generally, but also in law in particular. Because many of our data-driven, machine learning-based, deep neural network-based systems, a big issue is transparency, interpretability, and this is potentially a legal issue in the European Union's General Data Protection Regulation, as some of you know, GDPR, transparency of algorithmic decision making. So at least potentially, I think this framework, because it does have a logical language at the top, is potentially interpretable. We do have to extend the language. This is still in the category of future work. Remember I mentioned before, when we were looking at the quasi-logical form, QLF, that we see examples of events and actions and modalities over actions and epistemic modalities. So we have to incorporate that into this whole framework. Now, a lot of work has been done on logics of actions and modalities over actions, some of which I did a long time ago. Many other people have made similar contributions. And more recently, I think the best models for epistemic modalities, such as knowledge and belief, are what are called justification logics by Sergei Artemov and Mel Fitting, originally created by Artemov. But again, this is explained in the paper a little more, but this needs to be incorporated, or my language needs to be extended to include this, but there are clear handles, there are clear routes to do that, to extend this language in this way. And if you think about it, what I'm aiming for here, and this is the knowledge representation component summarized, it's an explanation of how legal concepts are organized, how to represent them, how to learn them, and that's one of the things that we need. Okay, so that's the claim. Okay, so how am I doing on time?
It's okay.
Okay.
We've got more time.
Okay, so so the next step. We want to combine the ICAL 2007 and the ICAL 2015 papers. That's the NL component, right? And the KR component. It's really a mature natural language technology, and it's a novel knowledge representation technology, which may or may not be the right answer. I don't know. It's my current theory, but there it is. We want to combine them, and now we want to, remember, we want to be this do this automatic extraction of that, the information in a structured case note from texts as automatically as far as we can go with an automated extraction. So how can we do that? Well, we're going to have to use now some kind of explicit machine learning technology. But what should it be? My claim is there's no way that fully supervised learning will work in this framework to extract something as complex as the components of a structured case note. Remember, you need procedural history, you need substantive legal concepts, and those are not simple labels. They are very complex structured objects. And the task of labeling a corpus with that much structure and extracting and learning that automatically, I think, is not going to work. So we need some other strategy, and that's why I'm talking about a semi-supervised learning strategy. And the idea here is, well, it turns out that we can do a good bit by hand to map the information from this QLF interpretation into the format of a structured case note using my language for legal discourse, right? A mapping from QLF to LLD. We can hand code extraction patterns for the components that we need. I've done a lot of it myself, just as an experiment. But of course, we can't scale that up to the size of the databases that thousands, hundreds of thousands of cases. So the idea is write the critical hand-coded extraction patterns for a collection, a sub-collection of the cases, and now generalize these extraction patterns by the unsupervised learning of the legal semantics implicit in a large set of unannotated legal cases. That's why it's semi-supervised learning. You have some labeled hand-coded extraction patterns, but you're trying to generalize beyond that using unsupervised techniques. Well, how do you do unsupervised learning? Well, this entire theory of differential similarity is really a theory of unsupervised learning. So that's the key idea here. Now, admittedly, here's the caveat. This is an ambitious research program. This is not done yet. This is just, gee, we'd like to do this. Let's try it. Will it be successful? Okay. So we don't know until we try. So it's clearly ambitious. I'll tell you 3 reasons, and these are developed in the article, in the chapter. 3 reasons to think yes. And this first one might seem a little strange. There is the distinction in every legal system between law and fact. Well, yeah, right? That's obvious, but what's the point? Well, my idea, the claim is, from a computational perspective, this means that there exists a level of abstraction dividing the concepts that we try to discuss systematically, that is the law, from those that we concede are chaotic and idiosyncratic, that is the facts. And what we're trying to do is to find a line between the law and fact, and we really want to extract concepts above that line. So there is some systematicity there, and we can take advantage of that if we can find that line, okay? First point. Second point, as we move up the abstraction hierarchy in the theory of differential similarity, now you have to read these papers again to really see what I'm saying here. We cycle back and forth between 2 geometries, a linear Euclidean geometry and a nonlinear Riemannian geometry. I mentioned before, the nonlinear Riemannian manifold is embedded in a higher dimensional linear space. And that cycling back and forth persists all the way up through the abstraction hierarchy. I can try to give you a picture of it. So that means that if we can find this line between law and fact, and again, these are in our hand-coded extraction patterns, if we really specify that, we can describe the lower-level concepts in LLD, my language for legal discourse, and give them an initial semantic interpretation in a linear Euclidean space. So that's part of the idea here. And now here's the key point. So there's increasing evidence that the semantics of lexical items can be represented approximately as a vector in a high-dimensional Euclidean vector space, using only the information available in the text. So this is word embeddings, which some of you may know of, and the people in Montreal are very active in developing these ideas. So here's the key is high-dimensional Euclidean vector space. That is a linear vector space. It's a linear vector space. So here's the famous example. There are lots of examples like this. So suppose V is a mapping from lexical items into some Euclidean vector space, R to the n, for some large n. Well, it turns out there's this linear semantics captured by the function, by the mapping V. The class example is V of queen equals V of king minus V of man plus V of woman. So what you seem to be getting here is a linear encoding of the underlying semantic space. That's the word embedding into a linear vector space. Now, here's the conjecture, and I'll say a couple more words about it, and I'm basically finished at that point. So the conjecture is that we can use these word embedding algorithms to recover the implicit semantics of legal texts. Now, what do I mean by recover? Okay, so fascinating question is, why do these word embedding algorithms work? How can you take the statistics from a text and get a linear vector space representation of semantics? Well, lots of people have ideas about what's going on there. To me, the most compelling analysis that I've seen, and I give two citations in my article, I give two citations to very recent papers that develop these ideas quite nicely, is what is going on here is, I have to be a little technical here, we are inverting a stochastic process that has generated a sequence of words from a latent semantic vector space. And that's why the word embedding algorithm is an inversion of this stochastic process. Now, that may or may not suggest something to you. It's explained in the paper, and I recommend reading the two articles that I cited in the footnote. And the reason why that's important for my approach here is my theory of differential similarity is based on exactly that model. It's a stochastic process operating on either a Euclidean space or a Riemannian space, and it alternates between the two. So I believe, this is the conjecture, I believe that I can use, I'm not just pulling the word embedding algorithms off the shelf and using them, and many people are doing that, and those are fascinating experiments. People should all be doing that. But I'm trying to figure out the mechanism underlying them and then applying them to my particular representation. And that is the QLF and the LLD represented in these Riemannian manifolds. So what I imagine is a stochastic process operating on my Riemannian manifold representations of legal concepts, generating the statistics you observe in the QLFs. And all I have to do is invert that process. So that's the strategy. You can see that it's fairly speculative, but I think it has some chance of getting some interesting results. That's basically the talk. If we go back to the original slide, this is my outline of the paper, and I've gone through, as you see, I've gone through section 3. If you read the full article, section 2 is basically earlier history of AI law. Again, focusing mostly on my work, but comparing it to some other people's work. Mostly on computational models of legal reasoning, which is what most people were doing in the field up at least through the 1990s. And then there's a section 4, where after developing what I call here a case study on semi-supervised learning of legal semantics, I try to generalize a bit further and apply some of the same ideas to some other legal technology ideas that are currently being discussed and applied, such as analysis of contracts, interpretation of statutes, not just cases, predicting legal outcomes, and so on. But I don't have time to say anything about that. But I hope I have motivated you to go back and read this article. And then what you should also realize is that this article itself is a summary. And if you really want to understand the subject, you have to follow the links to the original papers and other articles cited. I guarantee that you'll learn a lot if you do that. And so, again, I hope this brief talk has captured your imagination enough that you'll take on that challenge. Thank you. I think I went a bit over.
As you can well imagine, at least the lawyers amongst you, it's quite a challenge to comment on a paper that is presented by, I suppose, a world sommité in AI research. It's interesting because you have a sense of a work in progress, and you're tempted to say, let's meet again next year, we'll see how far you've come and what you have to deliver. Or come and spend some time with us and we'll talk in more detail. And I suppose I'm very glad that some of the, I almost say partners in the AI community within the university and within the university world in this city are present here. And so they see that in law too, very sophisticated things are being at least contemplated and tried. But as I said, it's a challenge to comment on such a paper. I couldn't possibly comment on the chances of success or alternate strategies that might be contemplated. So I thought what I might do is simply go back to where we came from and what were the questions that we asked on the way. This is maybe very simple and certainly not at the level of sophistication that you have been pulled into, but bear with me. So a long time ago, and we probably go back to the middle of the last century and even earlier, we faced the question of, or we were challenged, some of us were challenged by the question, can we represent legal reasoning by more transparent or predictable procedures? If law is a hermetic box, this is a reasonable question to ask. And what were the answers that we then were looking for? Well, there were people who were looking to legal logic, that is, adapting logical systems to represent legal content. And you had people in, a number of them in Germany actually, and you had Tamalo, who was an Estonian traveling to Australia. There were people at the time looking into what was called deontic logic, and actually one of the main figures in that field, von Richt, Finnish scholar, has been on one or several occasions present at the ACAL conferences. I think the ultimate, at least provisional conclusion about that, those attempt at formalizing law as a logical system so that you could develop algorithms to come to legal conclusions. The ultimate inference we made is, yeah, but law is not a closed and unambiguous language. In systems where we allow dissenting opinions, normally equally legitimate, surely you have to admit that several possible conclusions out of a configuration of legal facts and existing legal rules are possible. And that means that if you want to have a, in the traditional conception of a totally coherent legal system without gaps and everything, this doesn't work. And moreover, law evolves. Circumstances that justify a rule at a certain time may evolve so that we need a different rule, and then suddenly what we thought was a coherent pattern no longer is a coherent pattern. If we suddenly say, as we heard yesterday evening for those who were there, that animals, or animal beings as we now ought to say, are not things, well, this changes a number of things within the existing legal structure. Well, if you had nicely set that up as a coherent system, suddenly things are no longer coherent. You have to redefine things. So that challenge, I suppose, put the idea of representing law as a logical system for the moment on hold. And then in the late 1950s and early 1960s, a new device appeared, and that was a computer. And very quickly we understood that this is a general purpose information processor, sort of a reasoning machine in a general sense. There were people who had thought about this before, but it was not until the late 50s and 60s that we had a device that could actually do these things, however heavy it was at the time. And so we thought then, we changed the question that challenged us, and the question then became, can we facilitate lawyers' work and reasoning by means of that computer, by means of that device? And so what were the first things we looked to as potential applications? Well, we said at least one main challenge for lawyers is to find material relevant to the case they want to plead. And for those of you who have looked through the historical sections of the library upstairs, you know, until the 50s, we had sort of thick index books of cases, the L'évêque, and you had the Index Gagnant that would link citation linkages. They were good as far as they went, but surely it was still a very heavy procedure. So we had the hope of developing better procedures with computers. And so in a number of places, people started to say, well, can we put cases and statutes and regulations onto computers and then retrieve them as needed? Initially we thought, or some of us thought, that should be done by putting humanly prepared summaries on the computer, and that would then lead to more precise retrieval. But as you heard in the talk, if you want lots of human input, at some point the process becomes entirely unviable. So we fairly rapidly moved on to the idea we should put the texts as they were onto the computer and allow people to choose their own descriptors to retrieve things. That was basically the driving philosophy of the Datum project in this very faculty, which in due course was picked up or its line of development was picked up by Lexum, which Daniel Poulain was the main driving operator, if I can say, and now Canley, and everywhere else there are these Lee systems. So there is LII, the original LII, at Cornell, I think, Peter Martin. There is Ostley, there is a similar system in the UK. And all of these systems together form, I would almost say, a seamless web that allows us to have access to law as it is on the books in its formal sense, just about anywhere in the world. Yesterday evening, we would talk about a file being prepared for an injunction request dealing with the rights of animals, but not just here in this place, worldwide. We can now do this. This was inconceivable before. So computers have really made us given us an enormous advance over the way we could reason before. Things are now conceivable that were not at the time. Once these systems were going, of course, we refined them by saying, can we use computer procedures to improve the input? And of course, Lexum does that by recognizing existing citations to civil code or other codes, statutes, other cases, and so forth. It's a form of very simple intelligence, but it's not totally simplistic, and it helps the quality of the retrieval. We've also expanded that logic by saying, can we allow people to formulate their queries in a more intelligent way, rather than simply saying, this descriptor and that descriptor, brackets, or another descriptor? Should we not allow people to frame this in natural language, and then we interpret it in such a way that, and we can now do this quite comfortably in the legal systems, and you've mentioned a number of them, and of course when you go into Google, they have really refined that logic. But again, it's an extension of the idea of retrieving your base material, the information you want to work with. We've gone into further text processing. Once you say we can handle these cases, we can find them back. Oh yeah, but you can use computers for other stuff. At the time, this was called bill processing. Computers can handle all the stages of the adoption of a new bill, a new act. The stages, the changes from one level to another. The extension of that is to say we can keep a full historical record of what the statute was at any time in history. And just about everywhere in the developed world, we have that information. Just think for a moment, in 1950s, if you wanted to trace that information, what was the state of the law in 1928? You have a hell of a job to do it. Now it's like nothing. So that is quite an, how should we say, it's a gain for the sort of intelligence that that extends our ability to work. Then, of course, there is work on contract drafting. It started by saying, let's use boilerplate clauses, put them in the computer, and then just spit them out in the right order. As soon as you've mastered that thing, you might say, well, we can add a bit of craftiness to this, so that the system checks out whether clauses are compatible, whether a name that you give it in the beginning can be sent out throughout the computer. It might suggest gaps, it might suggest incompatible clauses, and so forth. That work is continuing, and apparently in practice extremely useful. Then a further question you might ask, and we did as we went along, can we use computers to better predict how judges will decide cases or should decide cases. One strand of research in the 60s and 70s said, well, if we know more about a judge's background or personality, can we relate that to the way they decide? And there was a very active research field for about 20 years maybe, mostly by political scientists more than lawyers, and that ended in, I've just noted here, Glendon Schubert brought out a book called The Judicial Mind, and that was sort of summarizing that research. I understand that Harold Spaeth is still continuing to feed a database that allows us to do similar things. But it's still a relatively distant cousin to the way lawyers reason. So another strand in that research was trying to predict what judges are going to do based on the content of the case. And there we get into the very first attempt to represent the contents of the case. How did we do it? Well, by sort of identifying descriptors that seem to control the outcome as lawyers would traditionally determine it, formulate them in a sharp way, possibly polarize them so that if the factor is present, then this will favor the plaintiff, and if it's not present, it will favor, it's a binary factor, it favors the defendant. You would then take a set of cases, analyze them by means of these descriptors, create description patterns, very basic, and then say, once you have the pattern, any incoming new case should be analyzed with the same machinery, and then you can see against the database we have by either statistical techniques or partial orders, which you mentioned in your paper, how this case might be decided. That's work done by, and you mentioned court, Reed Laurer. I was involved in that, and we published a paper in '74, Nearest Neighbor Revelations, anyway, about capital gains cases. But in the end, it's too labor intensive to really be very practical. In a sense, I think Kevin Ashley has taken the best ideas out of that research and pulled them further in the direction of AI. But you'd have to read his work to see how much. So if we want to do better, then we need a richer content representation. And so we need legal knowledge representation, and we should get closer to the way lawyers do reason or ought to reason. And that, I suppose, is the driving force of what we now call AI. We do try to simulate a certain image of what we think or of how we think lawyers do reason. It probably will turn out that lawyers, in fact, do not reason that way. As indeed in AI general research, we think that we do something as our brain does it. Of course, we discover very frequently our brain does things quite differently. But we do try to imitate the function, and these are functions that we think are specific to humans. That's where the idea of AI, I think, comes in. You've heard in the main presentation, of course, what the earlier research was, the deductive or rule-based models, the statistical models, and where we go from here. As you try to represent reasoning on a computer, you realize just how complex human reasoning is. It's not until you code that you become aware of just the enormous complexity. And in the case of our journalism, how much general world knowledge you need to be even modestly useful in a real life situation. And for legal reasoning, I suppose, that is just as true as elsewhere. And so when you talk about these case notes for a limited field, I suppose you limit, because otherwise the complexity is overwhelming. And for the moment, we do not yet have the wherewithal to expand this to enormous masses of case. The complexity before us is still daunting. Now, of course, but of course, in the earlier AI rule-based systems, expert systems, we try to create a knowledge base and then say, once this is humanly created, if we bring in new cases, can we then predict how these cases will be decided? The latest new dimension, which you have highlighted in very interesting ways, say, yeah, but creating that knowledge base is in itself a very interesting scientific challenge. How can we do it? What pre-existing structure do we need, and how does the mapping take place? And I found it interesting in the paper, and you mentioned it also in the lecture, to see that in that process there are jump discoveries. You mentioned the Collins thesis, 99 new passer, and suddenly a whole world opens up. It might be interesting to read the history of the development of AI as a series of jump starts, followed by much more focused stepwise development on the basis of those jumps. But that's just a further thought. Now, to conclude, what are we doing in AI? Are we trying to simulate human process, or are we drawing inspiration from what we think the human process is, but we are designing devices that only imitate some of the functions? Maybe that's what we are trying to do. We are not really imitating what humans do, and imitate human, that may be a purely scientific process. In the end, we're always trying to do what humans do and what we think is specific to human thinking, but in a device for a limited purpose only. And maybe that's what our ambition should be. If I may put an image on it, we know now how to make artificial limbs, in particular artificial feet. Now, the foot is a very complex organ, but we know now how to make an artificial connected to it, and so people can walk with an artificial foot. If you want to run with an artificial foot, you need the sort of device that Pistorius has under his legs. But that just shows that there are different ways of drawing inspiration from what humans do, and what type of inspiration, what type of imitation we're aiming for depends on what function we want to simulate. No more, no less. Thank you.
Thank you.